Alright guys, diving into 13.3, we're continuing on talking about triangles, dealing with our bisectors in triangles. Now remember, to bisect something means to cut it into two equal or congruent pieces. So what we see, we start talking about what you did in the solve it. So in the solve it, you connected three lines at one point. Whenever three lines or more connect at one point, they are called concurrent. And that point is the point of concurrency. Now we're going to use this in our special relationships that I alluded to in the last lesson, because we have two different points of concurrency that happen in any triangle. That would be the perpendicular bisectors will all always have a point where they meet, and the angle bisectors will all always have a point where they meet. So here's our concurrency of perpendicular bisector theorems. We see that if I draw a perpendicular bisector off each side, there will be a point in the middle where we hit. That is our point of concurrency. Just go ahead and color code that purple. And what that actually does is create a special relationship. Now if I go from that point of concurrency out to the vertexes of the triangle, I have three equidistant segments. So PA, PB, and PC are all congruent to each other. The other thing to know is that we actually call this point where the angle bisectors meet the circumcenter. Now why would we call it the circumcenter? Well, over here you can see if I have a triangle inside a circle, I can do the same thing if I use those perpendicular bisectors to find where these distances, these segments, would all be congruent to each other. Because PA, PB, and PC are all equidistant to each other, and I have this circle drawn out here, the point that is equidistant from every edge point is the center of my circle. So that's why we call this the circumcenter point, because if I talk about a circle being circumscribed about the triangle, that circumcenter is going to be the very center of the triangle. Now, depending on the type of triangle, you will see that the circumcenter may be inside the triangle, may be on the triangle, or may be outside of the triangle. And that is okay, because realize if we had an obtuse triangle and we tried to circumscribe a circle around this, actually give me a second. So I wanted to show you guys examples of this. If I make the center of my circle right there on the circumcenter and then expand out until I touch the vertexes, each vertex will be on the circle. Again, if I do that over here for the right triangle, expand my circle out until we touch the vertexes, you'll see, and I was slightly off with my center, but again, we are touching everything. Now the obtuse triangle is where people normally get a little bit confused. So we'll scale that up a little bit and see that if I start at the circumcenter, being the center of my circle, and then I expand out, again, every vertex is on the outer edge of that circle, which makes this point right in the center of your circle. So if you're still having any struggles on the got it, you need to have worked through the part 1 or problem 1 on Pearson so that this makes sense. But here on the got it, it might help to put this on a graph. And when we put this on a graph, we see that we have a right triangle. The other relationship that you could have seen to tell that is since two of my points had the same x values, we know that they are vertical of each other. And since two of my points have the same y values, we know that they are horizontal to each other. So A and B are horizontal, and B and C are vertical to each other. Now we look at this and see I have a right triangle. And what we should remember from our last slide here is that on a right triangle, the circumcenter will be on the triangle, and it actually normally falls on the hypotenuse. So if I look at drawing those perpendicular bisectors, I can figure out how long this is. Well, from 2 to 10 is a span of 8, so I go 4 over perpendicular bisector there, and actually I'm going to color code this. So let's use the green. We'll say this is our perpendicular bisector here. Then I come over and I bisect BC, and I find the perpendicular bisector there. And then I could find the perpendicular bisector of AC, but it is just going to go straight through that same point, because once we have two meeting and it's a right triangle, I see it's just going to be that point where they all met. So my circumcenter ends up being the point at 6, 5. That might be just a little bit confusing still, so please make sure that you try these following practices so that you work your skills up better. Go ahead and pause the video to try number 1, finding the circumcenter here. What you might notice first is that we actually have a right triangle. My slopes here are perpendicular to each other, which means I have a right angle, but in case we don't know that yet, let's just go ahead and start approaching the problem. we can make a perpendicular bisector here quite easy since this goes 4 positive and 4 negative. My y-axis is my perpendicular bisector, but just for good measure, let's go ahead and draw that on there. Now I see that my slope here is a -1, so if I go down 2 and to the right 2, I still have down 2 and to the right 2, so this is the midpoint of that side. And if I want to bisect it, I need to be perpendicular to it. So I can actually start up here and run a line perpendicular because the slope has to be, remember, the inverse reciprocal or the opposite reciprocal. And likewise, I can do the same thing over here, and I'm going to start up here so we can kind of see it, go perpendicular to it. And again, because this is a right triangle, my circumcenter falls on the edge, so my circumcenter is actually at the origin point. So there we go, our circumcenter is 0, 0. So here on number 2, I've gone ahead and put it on the graph. But if you have not done so yet, go ahead and try to find the coordinates of our circumcenter. So we see that again we have a right triangle, so we can anticipate that the perpendicular bisectors will meet at the circumcenter, which will be on the hypotenuse. So I go ahead and start with my 2 legs of the right triangle. I can bisect right here quite easily, and then I can bisect here. Well, I go from 5 to -2, so that's actually a span of 7. So half of 7 takes me 3.5. So I'd fall right there, and you can check it because you could come 3.5 up. And again, there we see that our circumcenter meets right on that line. I could go ahead and do my 3rd perpendicular bisector, but it is unnecessary. I go ahead and see that that point is at -3, 1.5. And there is our answer. Go ahead and work through the next section of the Pearson lesson and come back when you think you have the answer for the got it. Alright, so we're looking for a point that is equidistant from each of these trees. So the trees make up the vertexes of my triangle, and I know that a point that's equidistant from 3 points, that is actually your circumcenter. So to find our circumcenter, we're going to use perpendicular bisectors. So please make sure that you solve this out. I'm going to pause and do a bunch of work. So I did my work on the graphic from the image where we have triangle ABC, or you can look here at the answer from the book. Either way, we use our perpendicular bisectors, and once we find the intersection of 2 perpendicular bisectors, we know that the 3rd one will also bisect there. So we can draw it if we want to be very accurate and careful, or we don't always have to. So go ahead and try number 3 on your own. We want to find a place to put our recycling bin so it's equidistant from the snack bar, volleyball court, and the lifeguard chair. And again, what you can see here is it looks like a right triangle, so we can assume that it will probably be on the hypotenuse or very, very close to that if this is not quite a right triangle. We can find the midpoint between the volleyball and the lifeguard chair and draw that perpendicular bisector. We can find the midpoint between the snack bar and the volleyball court, draw that perpendicular bisector, and we find our circumcenter, so that is where we should place the recycling bin. If you want to see it not on the image, there is just the shapes. Now the special situation that happens with my angle bisectors in a triangle is similar to what we just did with our perpendicular bisectors, except instead of this point of concurrency being equidistant out to your vertexes, it is now equidistant to the edges as long as I take a perpendicular path from the edge into that into the point of concurrency, which if you looked ahead in your notes, or if you are right with us, we know that since that's equidistant out to the edges, we could inscribe a circle in here and see that that perfectly fits. It is also one of our big ideas coming up next. So this point we now call the incenter. So if it is the point of concurrency for angle bisectors, it is the incenter. Make sure you've worked through the Pearson problem relating to angle bisectors, and then come back when you believe that you have the answer for your got it. What I see is point Q comes from the angle bisectors of angle K and angle L, and since it is where the angle bisectors meet, it is our incenter, which tells me that QN, QM, and QO should all be congruent lengths. So when I'm given the length of QN and the length of QM, I can solve for X, plug it back in, and find the length of all 3 of the segments. So here, because I know that QM is equal to QN, I've set them equal. I then subtract 2x from both sides. I then subtract 36 from both sides and get 3x is equal to 15. I then divide by 3 and find that x is equal to 5, which I can plug back into either of these and find that my answer is 61 for the length of QO. Then we look at B. Is it possible for QP, so I'll highlight that for you, is it possible for QP to equal 50? So go ahead and explain that. And the answer that you hopefully got is no, because QP is not perpendicular with the edge of the triangle, and we know the line that is perpendicular is the shortest distance out to the triangle. So if I go not at a 90-degree angle, I'm going longer, and since I solved QN to be 61, QP is going to have to be more than 61. Now, number 4, we're looking for the point of concurrency for our angle bisector. So we're looking for the incenter. So I look for the angles that have been bisected. Well, this angle's been bisected and this angle's been bisected. So I follow their lines and I see that this point right here would be my incenter, which is point Z. So then in 5, we want to find the value of x. So check out what given information you have, how you can utilize it to find your value of x. Pause the video and come back when you have your answer. Because I see that R is my incenter since it comes from the angle bisectors, I know that RS will be congruent to RT since they are both perpendicular to the edge and they go to the incenter. So I start by setting up their expressions into an equation to state them equal to each other. I then use the distributive property to put my 4 into these parentheses and my 5 into this parentheses. I then combine like terms on my left-hand side. I then want to start isolating or combining like terms on a single side, so I decided to take this 4x away from both sides. So I get negative 6 is equal to 6x minus 30. I then add the 30 to both sides, getting 24 equal to 6x. And I find that my final answer is x being equal to 4. So number 6 is asking us for the circumcenter for the triangle at the right. You have to remember that the circumcenter deals with the perpendicular bisectors. So go ahead and try to figure that out. Again, this is a right triangle, so my circumcenter will fall on the hypotenuse. So I use the perpendicular bisectors of my legs and see that that circumcenter point is at 3, 2.5. Number 7, we want to find the value of x again. So analyze the information given to you, do all the math to solve it, and come back for the answer. The first thing we want to think about is our point of concurrency the incenter or the circumcenter? Since it comes from the angle bisectors, remember that is the incenter, which then tells us that the distances perpendicular from the incenter to the edge of the triangle are congruent with each other, so I can set these two binomials equal to each other and do the math to solve. So I start by subtracting the 3x from both sides, then I add the 24 to both sides, and then I divide by 2 to find my final value of x being equal to 6. So number 8, when we talk about a triangle's circumcenter, remember the circumcenter is the line that comes from the perpendicular, or the point that comes from the perpendicular bisectors. So when they meet outside the triangle, what type of triangle must it have been? And if you forget, you can look way back in your notes to this example right here where we see that my circumcenter is outside the triangle in an obtuse triangle. Number 9, take a second to think about why is it that we only need to find the intersection of 2 perpendicular bisectors? Why don't we have to use all 3? Hopefully what you're thinking is because when I find the point of concurrency for the 2 perpendicular bisectors, it will be the same as if we were to use all 3. So you always can use all 3, but once you find the point where 2 of them meet, you know that that is the circumcenter. So that is all that I have for you guys in this lesson. Please make sure everything makes sense. Contact me either phone, email, on Schoology, however you'd like. If you are having any issues with Chapter 13, please make sure you're doing your practice work and have a wonderful day.